Hi and welcome to this Leaving Cert Applied Maths video where we're going to look at impacts and collisions and specifically type 1, which are impacts or single body collisions. So within the impacts and collisions section, there are three types of impacts and collisions that you need to know. The first one are single body collisions or just impacts. The second type are direct collisions and the third type are oblique collisions. So the links to the other two videos are given in the description below. When we talk about the first type, so impacts or single body collisions, we're looking at a single particle hitting a barrier such as the ceiling, the wall, or the floor. So we're going to use a version of Newton's law of restitution to work on these questions, and that is that the coefficient of restitution, E, is equal to minus new velocity over old velocity. The coefficient of restitution is basically the fraction of which the speed will be retained. So for example, when you drop a ball on the ground, it will be returned at a slightly less speed than what it hit the ground. So that is a fraction which is known as the coefficient of restitution. When we're working with our impacts or single body collisions, we can also be asked about energy, and these formulas are given on page 55 of your log tables. We have the potential energy formula and the kinetic energy formula. So although we're looking at the course, the new Applied Maths course, which is first examined in June 2023, I am going to use some of the older exam questions to give us a sense of how this could be tested and to practice some of our skills. So the questions we're going to look at are the ordinary level question in 2019, it's question 5 part B. There's a higher level question in 2013, question 5 part B. And then I'm going to look at a higher level style question which is in the old textbook, so the Fundamental Applied Maths 2nd edition, which is exercise 7A on page 113.
So in this question, a ball is fired upwards in a room with a smooth horizontal floor and a smooth horizontal ceiling. The height of the room is 3.2 meters. The ball is fired upwards at a speed of 12 meters per second, and we can see that there on our diagram, from a height 1 meter above the floor. So again, we can see that on the diagram. The coefficient of restitution for all collisions between the ball and the ceiling and the ball on the floor is 3 over 5. And that's really important because that's not on the diagram. So find the speed of the ball immediately after striking the ceiling. And part 2 then says investigate whether the ball strikes the ceiling again after rebounding from the floor. So working on part I first, we need to understand all the different sections that are involved. So they want to find the speed of the ball immediately after striking the ceiling. So the first thing we're going to have to understand is its journey to the ceiling, and then it's going to have the bounce off the ceiling, and then we'll understand the speed of the ball. So I'm going to break this down into sections. So the first section I'm going to do is the ball travels to the ceiling. So I'll set up my V, U, A, S and T. We have our initial velocity is 12 meters per second. I'm taking upwards as positive. So that means acceleration, which is gravity, is working against us. I know that for ordinary level questions, we take gravity as 10, but since we're moving towards higher level, I'm going to keep it as minus 9.8. It has to travel a distance of 2.2 meters. That 2.2 meters because it's already a meter in the air. So we're going to try and understand the speed as it hits the ceiling. So to do that, we're going to use V squared is equal to U squared plus 2AS. And subbing that in, we work back and get 10 meters per second in our round. It rounds to 10. So we'll have a little bit of rounding because we're using 9.8 rather than 10 meters per second squared for acceleration. So the second section then is this bounce off the ceiling. So I'm going to use Newton's law of restitution, which is E is equal to minus new velocity over old velocity, or whatever version you want to use. I'm going to let x be the new velocity. So E is 3 over 5 is equal to minus the new velocity x over the old velocity, which was 10. Working that back, we get x equals minus 6 meters per second. That means it's going in the opposite direction. We took up as being positive, so it's telling us it's going back down, which makes sense because after it bounces off the ceiling, it's going to come down. So they asked us in the question for the speed of the ball immediately after striking the ceiling. So the speed is actually 6 meters per second, because remember, speed is a scalar quantity, so it doesn't have that positive or negative like the vector does. So the second question then says, investigate whether the ball strikes the ceiling again after rebounding. So now we need to understand a few more sections. We have the drop from the ceiling. We have the bounce on the floor. We then have the travel back up. So we have 3 more sections. So let's work with the third section, because I've continued on. I've said, right, it bounced off the ceiling. Now the ball is going to fall to the floor. So I'm going to have V, U, A, S and T again. This time, because it's falling to the floor, we are starting with 6 meters per second. In this section, I'm taking downwards as positive just to make life easier. The acceleration is positive 9.8 because then it's helping. I'm taking my S, the distance traveled is going to be 3.2 meters, and I want to understand what is the speed as it hits the ground. So again, I'm using V squared is equal to U squared plus 2AS. And I'm going to sub in here and work out V is about 9.9 meters per second. If you're using acceleration as 10, it'll work out exactly as 10 meters per second. So now we understand as it falls to the floor, what happens? I now know the speed immediately before impact. So what will happen as it bounces off the floor? So this is our fourth section. It's the bounce off the floor. I'm going to do something similar to what we've seen. The coefficient of restitution. So I'm going to use Newton's law of restitution here. So E is equal to minus new velocity over old velocity. So E is the same because it was the same coefficient of restitution for the ceiling and for the floor. So I'm going to use Y for my new velocity here. And when I work it through, I get Y is equal to minus 5.94. Again, it works out about 6. It works out exactly 6 if you're using acceleration as 10. So just bear in mind that we can look at the speed, but the idea here with that minus is it's going the opposite direction. But remember, we changed. We said actually now going downwards was positive, so it's telling us it's coming back up. The last section that we need to understand is the ball traveling towards the ceiling. So they've asked us investigate, and that leaves it very open. So it might be true, it might not. Investigate whether the ball strikes the ceiling again after rebounding from the floor. So I want to understand, does it have enough speed to get up to the ceiling again? So there's a few different ways you can approach this, but all of them will need us to go to our VUAST. So I'm going to set up my VUAST. And what I've actually done, and like I said, there is other methods to do it, is I'm going to see, well, when does the ball stop? And that will be its maximum height. And if the maximum height is less than 3.2, then it will stop before it hits the ceiling. If the maximum height is bigger than 3.2, it means that if the ceiling wasn't there, it would have continued on. But the ceiling is there, so it will have bounced off it. So there will be a strike on that ceiling. So I'm going to work here and try to understand the max height, which is S. So I'm going to use V squared is equal to U squared plus 2AS again. And I'm going to sub in and I'm going to look for S. So S works out about 1.8 meters. So based off that, that's less than 3.2, which means it will stop about 1.8 meters up. And that basically tells us that the ball will not strike the ceiling again. So make sure you answer the question as you were asked. Let's take a look at the 2013 question 5 part B. So this is one of the few single body collisions that we have seen, and it is the only one in recent years. So a ball is dropped onto a table and it rises after impact to 1/4 the height of the fall. Find the value of the coefficient of restitution between the ball and the table. Okay, so let's deal with the first part first. So we have this idea of a ball falling onto a table. So we've just done the ordinary level question, so you're going to see how this has then been brought up to a higher level standard. So we've got absolutely no numbers. We just have this idea of 1/4 the height of the fall. So we're going to talk about the fall in general terms. So we're going to start, because it's a fall, at 0, gravity is helping it down. We're going to say the distance is s. So when it does that, we need to understand, well, what speed in terms of g and s does it hit the table? So we're going to use v squared is equal to u squared plus 2as, and we're going to work through it, and effectively v is equal to the square root of 2gs. So it's going the same direction, so it will still be positive. We then have the bounce on the table. So just like before, we have E is equal to minus new velocity over old velocity. Again, I'm using x for my new velocity, and we get our answer for this bounce, the velocity that it leaves the table. We get this in terms of E. I've left it in terms of G and S. We now have a third section, and that's the ball rises off the table. Now in this section, what we know is that it will rise to 1/4 of the height of the fall. So we said it fell a distance of s, so therefore it will rise to a distance of s over 4. So setting up our v, u, a, s and t, we get v is equal to 0, u is equal to e root 2gs, we're taking that as positive, that was our answer from section 2. We take gravity as minus because it's working against it, and then s is equal to s divided by 4, where s was that distance of the fall. So now we can work this through, and v squared is equal to u squared plus 2as, and when we sub everything in, we can rearrange it. So we've subbed in, we're rearranging it. Remember, we're trying to find E. When we go and do this, because both of our distances were terms of s, the s's will effectively cancel, and we end up with E squared is equal to 1/4, which gives us E is equal to the square root of 1/4, so the coefficient of restitution is 1/2. So the second part to this question, if sheets of paper are placed on the table, the coefficient of restitution decreases. That is so important, by a factor proportional, the factor is proportional to the thickness of the paper. So when the thickness of the paper is 2.5 centimeters, it rises to only 1/9 of the height of the fall. Find the value of the coefficient of restitution between the ball and this thickness of paper. So basically, we're going to have the same section 1 and the same section 2, but the section 3 is going to change, and what's going to change is how far it rises. So this is V, U, same, A is the same. Now S, it's only 1/9 of the height, so it's going to be S over 9. And we're going to do the same thing we've done. V squared is equal to u squared plus 2as. We're going to substitute in, and then we're going to work through. Again, the s's should end up cancelling, and we get E is equal to the square root of 1/9, which is 1/3. Now, at this point, hopefully, you may have made a little bit of a connection. And that is, if we talk about a ball or a particle being dropped, and that is that there is no velocity being put into it, so this is dropping. What we've seen here is that if it rises to 1/4 of the height, that E is the square root of that. If it rises to 1/9 of its height, E is the square root of 1/9, which is 1/3. And that will help us because the next part says what thickness of paper is required in order that the rebound will be 1/16 of the height of the fall. So, clear this. If we talk about the coefficient of restitution, using that idea, the coefficient of restitution E is going to be the square root of 1/16. So that will give us E is equal to 1/4. Now, if you didn't cop that, you could have gone and done that section 3 a third time. There's absolutely no problem with that. But we have seen just this little shortcut. So E is equal to 1/4. So this is kind of gone beyond our what we need for question 5. We're really talking about understanding, and unfortunately my highlighter has left. So I had the idea of decreases and the factor proportional to the thickness of the paper. So this can be it can be quite hard to understand, so we'll try work through it. This is the idea of the ratio of proportion. We're trying to understand the thickness if the rebound will only be 1/16. So what happens is, as the paper thickness increases, we get a decreasing in the coefficient of restitution. So it means it doesn't go as high as it would. And that factor is proportional to the thickness of the paper. So let's set this up in a way that hopefully makes sense. So we're going to let the factor be k times the thickness, because I'm going to have some factor that's proportional, so it's going to rise as that thickness rises. So it's k times the thickness. You can call that another letter if you prefer. So it's decreasing, which means effectively it's going to be the reciprocal. So we're not going to multiply it by this factor. We're actually going to divide it because it's going the opposite way. So we're going to use our reciprocal here. So it's going to be 1 over k times thickness. We need to work with what we know. So what we know is, and I've used part 1 and part 2, so hopefully we can keep track. The coefficient of restitution in part 2 should be the coefficient in part 1 multiplied by this 1 over k times 2.5, because the thickness was 2.5. And this will allow me to set up a little equation to find this k, this part of the factor that I'm missing. So I get a third is equal to 1 over k times 2.5, all multiplied by a half. We can use the reciprocals here, which is easier, so just flip the whole thing. And I can work out k is 3 over 5, or 0.6. So that gives us k. So now we have a better understanding of the factor. So we're going to do the same thing again, but this time we're going to use the coefficient of restitution from part 3, which we've worked out as a quarter, and we're going to use this 1 over k times the thickness, but this time it's the thickness we don't know, times the coefficient in part 1, and that works out as a quarter is equal to 1 over 3 over 5 times x times a quarter. Just like the previous part, we're going to use the reciprocals to help us, so we're going to flip it. And when we flip it, we get 4 is equal to 3/5 times x times 2. And when we work that out, I think we get x is equal to 20 over 6, which simplifies down to 10 over 3 centimeters. So that little piece there was quite a complicated little piece, but not because it was the impacts and collisions. It was really that understanding of it was trying to understand that inverse proportion and how we can deal with it. So it's a good one really to go back over for maths as well as applied maths. We see it in science as well, this idea of inverse proportion. Next we're going to look at a book question, and this has come from the Fundamental Applied Mathematics book, edition 2, and it's from chapter 7, so exercise 7a, and it's page 113. So a smooth metal sphere falls vertically and strikes a fixed smooth plane inclined at an angle theta to the horizontal. If the coefficient of restitution is 2/3 and the sphere rebounds horizontally, calculate the fraction of kinetic energy lost during impact. So although this is falling, we don't need to take account of the section of falling, and we're going to go straight into the bounce. In order to do that, we need to take a quick look at this diagram and see how we're going to be able to change it to be workable for us. So the first thing I'm going to do is I'm going to say, well, actually, because it rebounds horizontally, we have alternate angles, so there is theta. We also have 90 minus theta here. Oh, my theta's gone a bit funny, because this is a right angle because it falls vertically and then rebounds horizontally. So just like any of our inclined plane questions, once we've dealt with gravity, which we don't need to in this question, we simply rotate it so that the plane is horizontal. So we're going to rotate this and it'll look like this. So I'm going to put my theta back in here, and then this is 90 minus theta. So what we can do at this point is then say, well, I can now resolve u and v using the angles that we have. So u, we talk about it starting up here, and our angle will match that angle there. So we'll use 90 minus theta. For v, it's like this, and there's our theta, so we'll use that. So u is minus u cos of 90 degrees minus theta I minus u sine 90 degrees minus theta j. However, to simplify that, because that is not particularly nice, we can change and say that, and I'll put it up here, we're going to say the cos of 90 degrees minus theta is actually the same as the sine of theta. And the reason we can say that, and if you want to do a bit more exploring on this, draw a little right angle triangle and take any two angle values, preferably not 45 and 45, because obviously that's not going to be hugely helpful. Maybe 30 and 60. Look at page 13 of your log tables and 30 degrees and 60 degrees, and you'll see that the cos of 30 degrees is the same as the sine of 60 degrees, and so on. So having that idea that when the angles add to 90, there's a symmetry there where the cos and sine of the angles would then be equal. So I can replace this complicated looking thing with a much easier minus u sine theta I minus u cos theta j. Much easier. So then we have the velocity of the rebound, and that's v, and that is minus v cos of theta plus v sine theta j. So really do watch your signs there. Now, I'm going to think about this as an impacts question. So if I was thinking about this in terms of my impact, I could take what I already know about the velocity before it hits, so i.e. looking at this here, and I know because the plane that it hits is now an I, it matches what would be the I axis, we know that there would be no change in the I direction. There would only be a change in the Y direction. So another way we could write V would be minus u sine theta I, and then there would be a change in the J direction, so we could call that just like xj. So remember, there's no change in the I direction because the barrier, in this case the plane that it hits, mimics the I axis. Now you might say, but it didn't in the original question, but we've rotated it and we've also resolved the vectors taking that as being horizontal. If we were to look at the vectors that would have been in the initial question, they would have just been i's and one just j's. So for example, u is just a negative j, v is just a negative I, but we've counteracted all that and we've worked with that. Let's work out that x using our Newton's law of restitution formula, which is E is equal to minus new velocity over old velocity, and that is 2/3 coefficient of restitution is equal to minus x minus new velocity over the old velocity, which is minus u cos theta. I'm only working in a j direction because remember the i's have not changed. So working that through, we get x is equal to 2u cos theta over 3. So now we have two versions of the j direction which we can effectively equate. And this will allow us to write u in terms of v or v in terms of u. It doesn't really matter which way. So we have 2u cos theta is equal to 3v sine theta. And at this point, there's a few different things that you can do. Because we don't know what theta is, we're going to need a second equation to help us. So the second equation is going to be the i's. So we've worked with the j's. Now the i's are a little bit easier because we simply have to let them equal. So effectively what we have is v cos theta is equal to u sine theta. Now originally they were both negative, but the two negatives equal mean the two positives are equal. So now we have two equations. We have 2u cos theta is equal to 3v sine theta, and we v cos theta is equal to u sine theta. Now you can work with these whatever way you want. However, the easiest thing to do is actually to simply divide the first one by the second one. And we end up with the cos square, or the cos theta is cancelling, the sine theta is cancelling, and we end up with 2u is equal to u divided by v is equal to 3v divided by u. We can then work out v squared is equal to 2/3 u squared, and that's important because what they've actually asked us is about kinetic energy. So we're going to need u squareds and v squared. So kinetic energy before is a half mu squared. Now where u is the whole speed rather than the velocity, which has been resolved into i's and j's. So I'm going to leave that as is. And then for the after, instead of v squared, I'm going to sub in what we have here, which is 2/3 u squared. Now, by doing it this way, we get a really nice little bit, just a really nice little quick answer, because I've just rearranged this to say that that's the same as 2/3 a half mu squared. So basically, the kinetic energy after is 2/3 the kinetic energy before. And the question here asks us to calculate the fraction of kinetic energy lost during impact, and the amount that's been lost is actually 1/3, because if the before is full and then after is 2/3, then it must have lost 1/3 of the kinetic energy during the impact.